Dar gracias a los que están esperando. Pronto comenzaremos con la charla.
Okay. Dear all, welcome to the seminar of Classical and Statistical Physics at the Group of Complex Systems, Department of Physics, University of Guadalajara. Today our speaker is Dr. Cros. He is from this university itself. She did her master degree from Lyon in 1998 on statistical physics and nonlinear phenomena. Then she did her doctoral degree from Mediterranean University in Marseille, France in 2003. Then she did a couple of postdocs. Her first postdoc was from University of Sao Paulo, Brazil, from 2003 to 2005. Then she did her second postdoc from Instituto de Física, Autonomous University of San Luis Potosi, from 2005 to 2006. Then she came here as a researcher and professor in this university, and from that time she is here. Today her talk is guidance in the system.
Thank you. Thank you for inviting me. I will speak about a research project that I began since I arrived here in Universidad de Guadalajara. So I will speak about the sky dancer. The title is Sky Dancer Complex System. So what is a sky dancer? This is this kind of fabrics made large tube which dances above an air blower. And everybody has seen one in the street. It's for advertising. And I began this project because when I arrived, there was no experiment about fluid mechanics. So this was a simple one to begin because we need only an air pump and a soft tube that we can make ourselves with plastic fabrics that we buy, and we seal it with the head. And we need a video camera. So I began this project also because I'm interested by the area of fluid structure interaction. This area is about the interaction between a flow and a deformable structure, like the garden hose. This kind of hose, flexible hose, which conveys water, and when the water flow is high enough, the tube begins to fluctuate. I think that everybody has seen too in comics when the firefighters want to switch off a fire and the hose begins to fluctuate. Another example of fluid structure interaction is when the wind turns the pages of the book. This is what's studied too. And the classical problem is that of a flight which fluctuates in the flow. So the flow does not need to be turbulent to make the flag fluctuate. With the laminar flow, the flag fluctuates too. It is because of an instability which is called aeroelastic instability. So it's an instability where two competing processes happens. The elasticity of the flag, of the plate, and the flow. So the flow wants to destabilize the structure, and the flexibility, a low flexibility, so a high rigidity, will prevent the structure to deform. Okay. So the aeroelastic instability okay. So this instability happens too in the plane wings, and that's why this instability was studied since the 1960s, because in fact two Electra planes fell down because of the instability. So each time a new prototype is built, a new plane prototype is built, it is necessary to estimate this kind of instability and to make experimental tests to prevent this kind of thing. So I will present theoretical works which have been done before my work. So this is the aeroelastic instability for a flag, and this work is from Christophe Edouard, who collaborated with me in the work I will present to you. So this is a flexible plate. The span is h, chord is L, and airflow comes to the flag, and the flag can deform with a transversal deflection, which y, which depends only upon x and t. So the deformation is the same in the whole span. The equation which describes this motion is this one. This is a fourth-ordered partial equation. So y is the transversal deflection, rho p is the mass per unit area of the plate, and d is related to the flexibility, to the plate flexibility. E is the Young modulus, and nu is the Poisson coefficient. Okay. So, T is time. So y depends upon x and time. So this part of the equation is not difficult to solve. The complex term is this one, because this is the pressure difference between the two faces of the plate. So to estimate this term, each author makes a different hypothesis and develop the solutions in a different way. So in this work of Eloi et al., the first thing to do is to make the equation non-dimensional. So this equation writes like this one, and there are three non-dimensional numbers, which is the non-dimensional velocity, the mass ratio between the fluid and the plate, and the plate aspect ratio. Okay, so in this work, Eloi wanted to estimate the threshold velocity above which the flag begins to flap. So for velocities higher than UC star, the flag flaps, and below this threshold, the flag does not flap. So this is the aeroelastic instability threshold. Flapping, it's a periodic oscillation.
Just moving, if it's just oscillating, that's normal, right? Flapping, if it...
No. Flapping is oscillating, is the same thing. This image is the superimposed image of the profile of the plate, see from above at different times. Okay, so this is, I call it flapping or fluctuating or oscillating. This is the instability.
Together, I mean, it would oscillate so much that it starts to hit.
Okay. No. Okay, and now the same instability happens in fluid conveying tubes. This is a case, so this is an old study made by Paidusi, who is the person who developed this area. So for a tube, now the fluid goes through the tube with a velocity u. We have still 3 non-dimensional numbers. So now we have the non-dimensional velocity, as in the previous case, the mass ratio between the fluid and the tube, and now we have the ratio between the on weight of the tube and the flexibility, the rigidity of the tube. And in this case, when the tube is fixed from its bottom part and the air go upwards, so this is the case when gamma is negative. Okay, so we are in the configuration when the tube is like this. The air flows upwards, and so when we increase the velocity, first of all, the tube does not have the flow is not high enough to make the tube stand up. So the tube collapses because of its own weight. This is this region. After that, the tube can be stable. Here it is vertical and it is static. And for higher velocity, the tube will fluctuate. Okay.
The previous case, this the plot you show us, that depends also on the rigidity of this
yes,
plane,
it
right?
is hidden here. Yes, the D is related to the rigidity.
So in higher values of UC, one will expect that these oscillations happens very quickly,
Yes.
with very small velocities.
Yes, if D is low, the plate is more flexible, and the UC will be lower.
Translated into this case, this is represented in gamma, right?
Yes, this plays the role of the non-dimensional velocity of the previous slide. This one.
This rigidity of the material, this goes in gamma, I guess.
It appears here and here. Yeah. Now it is called EI. Okay. These are the only equations I will show today. Now there are experiments. Okay. So with the sky dancer, so we made a small sky dancer that we can have in the lab. And the difference between the sky dancer and the tube, the flexible tubes which were studied before, is that the flexible tube may curve, but the soft tube, which is made with plastic, with fabrics, can fold, completely fold. Okay, this is the main difference. So when I switch on my air pump and I begin with a low velocity, the tube collapses because there is no air, so it collapses. When I increase the velocity, the tube rises, and for higher velocity values, the tube will dance like in the street. This is a plastic fabrics.
These fluctuations, this happens in the last, is the case of the last picture.
Yes. I will show a video now. And to study, to know if this kind of soft tube behaved as a flexible tube, it was difficult because of this state. So we chose to put the experiment upside down. Like this, when there is no flow, the tube is straight, so it begins to fluctuate from this straight state, and we were thinking it would be more easier. Okay. So we put the air pump fixed to the roof, and we switch on the air, and what we see is this kind of fluctuations, which do not seem periodic, they seem chaotic. And for this configuration, this is a long tube, longer than 1 meter and 20 centimeters, diameter 1.6 centimeters. We saw this kind of states. And here for the video, I chose a state which remain a few seconds, but the tube may remain like this several minutes.
And this is at the same speed of the airflow.
Same.
Or is this the velocity is changing continuously?
No. Okay. This is a thing that I will speak about. Yes, I will speak about this because I do not control the velocity inside the tube. I control the electric pump power, but I do not control the velocity. But here, when I took this video, I didn't touch anything. I put the pump power at a fixed value, and I recorded the video. And this, we can observe several kind of static states, as I will explain now. Okay. Okay, so I will speak about two works. The first one is about the alternance between turbulent and laminar phases. Like we saw, the tube fluctuates and remains in a bizarre state and fluctuates again. So this is intermittency. And after that, we will analyze the zig-zag stable states. So the first work is about intermittency. And first of all, we wanted to record the tube behavior without having to record videos, because videos take a lot of memory in computers. So we wanted to have a signal, a simpler signal. So what we know is that at the pump exit, when the tube is long, there is a pressure drop. That is to say that when the tube is long, the pressure here at the free exit, at the free extreme of the tube, is equal to the atmospheric pressure, and the pressure here must be higher, so that there is a flow which goes from here to here. And moreover, if there are faults, like here and here, the pressure, the difference of pressure between this point and this point increases. And the pressure drop is higher when the angle is sharper, right? So if the angle is sharper, the pressure drop is higher, okay? So what we did is to put a pressure sensor here and at the same time an anemometer, hot wire anemometer. So we could measure at the same time pressure and velocity, the air velocity. And what we observed is this kind of curve. Pressure is the blue curve and velocity is the red curve. What we see, so this is pressure and velocity when the tube fluctuates. What we see is that pressure increases and decreases. And when the pressure is high, generally the velocity is low. Okay. It's logical because when the tube falls, the pressure will be higher because the pump must use more pressure to evacuate the air, and the flow is obstructed, so the velocity decreases. Okay. So when the pressure is high, velocity is low, and this is coherent with the characteristic curve of a bomb. The characteristic curve of a bomb, of an air pump, excuse me, a pump, is this one. So I can put my hand here at the pump exit to prevent the air from flowing. So I exert a lot of pressure and the velocity will be 0. And if I let the exit free, the pressure is 0 and the velocity is maximum. So for the same electrical power, there are all these states which are allowed in function of the what succeeds here. Okay. What I do when I change the pump power is to change this curve, but I don't control the velocity inside the curve, inside the tube. No. And since we have two signals which means the same thing, I will see faults if I take the velocity signals or if I take the pressure signal. I chose to use the pressure sensor because the anemometer is very delicate. The hot wire is a thin wire of 1 millimeter long, and it has a diameter of a few micrometers, so it can break with anything. So we chose to use pressure and to record the pressure for different experiments. So we recorded pressure. We let the tube fluctuating during 2 hours and 30 minutes to have a lot of statistics. And because, as you see, well, I will say it later. We took experiments. We recorded signals for 4 different pump power values. And this is a signal of the pressure, but along 200 seconds. So what we see in these signals is that the pressure is constant and it has burst fluctuations, and it is constant again yeah, etc. So we see that this more or less constant signal corresponds to the stable state when the tube is static. And when the pressure fluctuates, it means that the tube fluctuates. So this signal is typical of an intermittent signal. We will call these regions laminar regions. So the tube is static. And these regions, the turbulent phases. So this kind of regime is called intermittent regime. It is one of the three routes. It is one of the three classical routes to chaos. When a system is laminar or periodic or static, and we increase control parameter, classically the system can take three different scenarios to reach the chaos, and the intermittency is one of them. So here we increase the pump power, and here are the four different pressure signals. We see that when the pump power is low, the laminar state is long. Okay, the tube does not fluctuate a lot. Then it will fluctuate and come back to a laminar state, and so on. When the pump power is increased, the laminar state is shorter, and it alternates between laminar phases and turbulent phases. And for the higher value of the pump power, the signal is turbulent, and there are very few laminar regions here.
I suppose there is a regime in which the pump power is low enough, so there's always steady.
Yes. Yes. So what we do to characterize this kind of regime, we binarize the signal.
So when you switch off the pump, so just for the gravity, it will be straight, right?
Yes.
And then if you're low pump power, it will be also straight, which is laminar flow, and then it will slowly get turbulence. So whenever you are changing the pump power, you see quite a bit of change, or it change continuously?
Between, I don't know what you mean by abruptly or.
So for example, you have a low pump power or no pump power, it's straight, and then you switch on the pump, right? So then you immediately, for a fraction of time, for a short amount of time, you see the turbulence, and then it becomes laminar, or it change. This doesn't happen. Or if you change the pump power from low to little high, okay, so then you, for a transient amount of time, you see the turbulence, and then it becomes laminar, or it remains laminar and slowly changes.
When I change the pump power, if the pump power is low enough, I can move the tube from its straight shape, and it will come back to the straight shape. But for higher pump power, I move it, and it will fluctuate. No. Oh, here I don't show the whole signal, and before this there was fluctuations. So we binarize the signal, and the laminar state stands for 1, and the turbulent states here when there is a fluctuation the fluctuation, we put it to 0, and we will measure the laminar times, the laminar durations, and we will measure the turbulent durations, and we will do statistics. So we do it for the 4 signals. And what we see for the laminar duration is this kind of histogram. So for the laminar durations, I don't know if you are used to see this kind of diagram. This is the probability that laminar duration is greater than this time. So the probability that the laminar duration in my experimental signal to be higher than 1 second is 1, because all the laminar durations are higher than 1 second. And the probability to have laminar duration higher than 10 is lower. This is the probability of 0.1, 0.2, 0.3, 0.4 or 5. Okay, and that's how we build an histogram. Okay, so we do it for the laminar times and also for the turbulent times.
There's no information with the power pump in here, or should go somewhere?
I have 4 histograms of this for each power, and 4 of this. Yes. This is an example.
This is the low power.
This one, I think this is the second or the third power. This one. But what we see is for all the histograms, for all the pump power, we have an histogram which is more which fits more likely like a power law. And for the turbulent ones, it fits more likely than an exponential law. So these kind of histograms are used to identify the kind of intermittency. So what we decided is to compare our experimental result with a probabilistic model.
Pump power, or you have a specific?
This model is independent, but we will interpret our experimental model with this model.
But experimentally, you also see this behavior as independent of pump power?
Which behavior?
This power law behavior.
Independent? Okay, the distribution is the same. K changes. When the pump power changes, K changes. But this is, the laminar durations are always algebraic, and the turbulent durations are always exponential. So this is a work done by collaborators, and the work they did is they have a probabilistic model where x is their state variable, and this state variable can can be greater than or smaller than a threshold. If x is smaller than y, which is a threshold, we say that the system is laminar. And if x is greater than y, we say that the system is turbulent. And the new ingredient of this work is that the threshold may fluctuate or not. the threshold can fluctuate with a probability. So I will show to you a diagram after that. So the state variable x belongs to this interval and have a distribution of probability, which is exponential. And y has another distribution of probability. And now we will have a parameter mu, which is a probability which will allow the threshold to vary. If mu equals to 0, the threshold always varies, and mu equal to 1, the threshold never varies. So for the initialization, we choose x0 and y0, and we compare them to see if the system is laminar or turbulent. In the next step, we choose xy with its probability, and y we allow it to vary with a certain probability. And if it varies, we choose a new value y with probability j, and if not, it keeps constant. So in this diagram, I think it will be clearer. When mu is equal to 1, the threshold is constant, and x varies in each step. So here, x x keeps a value which is below the threshold, so we are in the laminar region. Now x is greater than y, so we are in the turbulent region, and after, when x is again below the threshold, we are in the laminar step. This is when mu equals to 1, the threshold is constant, and mu equal to 0, the threshold varies for all the steps. And this is the same thing when x is lower than y. We are in the laminar region, and x is lower than y. Higher than y, we are in the turbulent region. So the advantage of this model is that we can easily calculate the probability that a laminar time has a certain duration t. So I don't know if I take time to precise the calculus, or I give the results. So to calculate this probability, we do this kind of integral, and we will obtain a probability which has a power law, like in our experiment for the laminar time. This happens when the threshold is constant, and when the threshold always varies, we find probability as an exponential. So we can interpret our experimental results with this model. I remember you that the laminar durations are algebraic, with an algebraic law, and the turbulent duration as an exponential. And the interpretation is that during a turbulent state, the threshold will vary simultaneously to the state variable. And the physical interpretation is that the threshold Y of the model depends upon the tube shape and its inertia. So in a turbulent state, it always varies. And in the laminar state, it is more constant. To our experimental results, we could extract the tau, this parameter with the fits, and k, the power of the time. So what we see is as expected, when the pump power is increased, the laminar time have more probability to get longer, while k has a strange behavior because for the first three values, k decreases, so it means that the longer laminar durations are less probable. But at the final, we see that k is higher. We could not interpret it, but what we wonder is that if all the laminar states are the same. So what we did is to observe the laminar states, and as I told you before, we see that the tube stays in the zigzag shape, which is different from one zigzag shape to another. And if we measure the mean value of the pressure during the duration of the state, we will see that the pressure for this shape is higher than the pressure for this shape because of the angles. The angles are sharper, so the pressure is higher. And so we wonder if finally the laminar, we considered that there was only one laminar state, but we could consider that the laminar states are various in the experiment. And so this is an histogram of the mean value of the pressure of all the laminar states in our experiment for the lower pump power value. And what we see is that there are a maximum here, and here there are a very small maximum. And we chose to say that there are more or less three laminar states which are separated. We can distinguish them by the pressure. Okay. So what we did is to take again the pressure signals, and now, as a function of the pressure value of the laminar state, we will consider if the state is 1, 2, or 3. So the laminar pressure 1 is for low pressures. Laminar state 2 is for intermediate pressure values. And laminar 3 is for higher pressures. It corresponds to sharper angles. Okay? And we have the turbulent. And if we do again the statistics, we can see that for all the pump powers, the one, so the lower pressure value, has a probability the probability for the low pressure states to stay a long time is very small. Okay, the probability for the low angle, no, the small angle, the probability of this kind of states. Where was it? No. Oh, I get lost. Oh, excuse me. Ah, this one. So this one will stay like this short time, and this one has more probability to remain like this long time. Okay, that's what shows this kind of histogram. And we can see that each one of these states has its own distribution. And these are the K values. So for the smallest pressure state, K is very high. It means that the time are short. And for the intermediate state, K is intermediate. And for K, this is the state which has a longer life. Okay. So this is the conclusion of this work on intermittency. What we did is to interpret the different distribution of the turbulent and laminar states, and we found that the laminar regions are constituted by 3 different states which have their own distribution. So this is a work which has been published. And no, I don't know if you have some questions. It is difficult, or I don't know if. I
just was thinking that the two cases for stable states, the one which has the lower pressure, it may be that the reason that it lasts the less is because of the gravity, because it has wider angles, so you have more torque in the fabric legs, to say something. So maybe gravity plays a role there. Lasts the less.
I don't know if it has more torque. I think that I would say that it depends more on the deformation of the tube. What we was observing is that when the tube was very deformed, it could be more stable because there was because of the material. Yes. And now, if you want, I don't know if I have time. Yes. Okay.
So Jose Carrera asked, when binarizing your signal, how do you decide that there is a turbulent behavior? Because it means that depends on the scale. I mean, if we see close enough, all that will be see are fluctuation.
Okay. See, to binarize the signal it's always a subjective criterion. So I choose a criterion to binarize the signal. I don't remember. I think we. Yes, I don't remember exactly what we have done, but indeed, it's a criterion that with this criterion, we will lack some laminar states, and sometimes we will consider some turbulent states as laminar. It's like this, but we chose finally criteria so that the most possible the signals we agree with what gives the signal. It's subjective. So I don't know if it answers the question. So now what we want to do is to model, to analyze the zigzag states. So here, what we want to say is that these zigzag states are the first time that we see this kind of states in the system. So this kind of system, I spoke about it in the introduction. And a study which is similar to the flexible tubes is a system of n-articulated rigid tubes. So there are rigid tubes, and there is a fluid which is conveyed inside them, and articulation. So the first theoretical study was done a long time ago, but there is an experimental study which was done a few years ago with 5 rigid tubes which are maintained by plastic articulations. So what we did experimentally, this is a work, this is a master thesis of Oscar Donato. And what he did is we have the pump here, the tube here, and so he was taking the tube here, and it moves it. And he let it go, and he's observing if it is stable or not. When it is stable, it takes a picture, and when it is not stable, it tries another length and other angles. So what we observed is that the tube, when it is stable, it has always 3 roughly straight segments. So we can characterize this profile thanks to L1, L2, and L3, the tube length, the segment length, and their angle with respect to the vertical. And we note it in the computer. And here we plotted the stable states. So these are the zigzag states. And we need only 2 parameters, because if we know L1, L2, we know L3, because the total length of the tube is constant. So what we see here is that a grid range of L1 is allowed. We can have from 0 length here to 80% of the total length. For L2, the range is smaller, because L2 we will see that this angle is higher, so it costs a lot of energy to incline this segment. So L2 can go from 10% to 40% of the total length. And for the angle, so what was I saying is theta 2 is higher than the other 2 angles, and theta 1 is always as generally an opposite sign to the other 2. That is to say that theta 1 goes leftwards, and theta 2 and theta 3 go rightwards. Okay, So this is to balance the weight of the system. And now to model this system, this is Eloi, the author I spoke about sooner, proposed to model this system with a system of 3 articulated rigid tubes. So this equation was established by Benjamin in 1961, and L is the Lagrangian. And the total Lagrangian of the system is the sum of the Lagrangian of each segment. Okay? And the Lagrangian of each segment is the kinetic energy minus the potential energy. And the kinetic...
That in the articulations there is not change in the pressure, then it's the flow goes straight, nothing.
Yes. The flow does not go straight.
It does. I mean, it means that these Lagrangians do not depend on the other. H1 or they do.
H1.
I mean, if
There is interaction between the distinct segments of the tube.
They are connected, so there is a connection, a physical connection.
That doesn't have to do with equations of motion that appear there.
It is well, finally, if this one oscillates, this one also will oscillate. So. Okay, so here the Q will be the angle. We will fix the tube length, and we calculate the tube kinetic energy. So this is.
The question was whether the U is constant in this model.
Okay. Yes, it's constant. Yes. Mm. Yeah, this is a model, and I think that this fact explains the differences between experimental results and the model. So we did the calculation, so it's not very difficult, but it's a large equation. We put it in MATLAB, and MATLAB can solve the system of equations. And now what we added in order to see the zigzag state, because if we let the system like this, we won't observe any zigzag state. So what we added is a torsional spring at each articulations. So this torsional spring comes from the fact that the tube can fold, and to estimate this spring constant, we consider that we fold the tube and we calculate the weight of this portion and the angle this portion was inclined. So thanks to this, we can estimate a torque, and we will fit the experimental torque with this kind of law, because there are 3 advantages. The first advantage is when theta tends to 180 degrees, that is to say that the fold is complete, there is a divergence, because experimentally it is not possible. When theta tends to 0, it's linear, because we like, generally, when for small angle, there is a linear behavior. And this expression is integrable, because we will have to integrate tau to have the potential, the spring potential. So we made the measurements to have the spring constant, and we have all these experimental points, and we feed them with the law I showed you before. But when we put it in the model, we didn't find any zigzag stable state. So what we did is to take the tube with a flow, okay? Because with the flow, the torque will be higher. So we put here is the air pump. This is a rigid tube, and this is a soft tube. And we did the same kind of experiment, and we see that the values of the torque are 60 times higher than
difference between both experiments?
here. There is no airflow inside the tube, and here there is an airflow. And when we put the potential here in the model, we found different regimes. So these are the simulations for a constant flow of 10 meters per second. This segment has the same length, and we change only the length of the two bottom segments. So when L2 is small, we see that the system tends rapidly to the straight vertical state. Now I increase L2, and what we see is that the systems oscillate without damping. And the third configuration is what we wanted to see. Okay. So we found the zigzag state, and if L2 is higher, the zigzag state is not stable anymore. So now we explore all the value of L1, L2, and L3, and this region is where we found a stable zigzag state with our model. So it's a little bit different from the experimental data, but this is a new result. And as for the angle, the model gives an angle which are similar to the experimental data. So the conclusion is that we experimentally describe these zigzag states, and we could reproduce them thanks to a model which is constituted by 3 articulated rigid pipes. And this model shows a great variety of regions. So that's all. And the last thing is that the last thing I wish I could find. Now I hope I could explain this kind of wave which travel along the sky dancer.
Somehow realized that you changed the power only a small amount.
Yes.
Double the power, for instance, or you did not want to, or you know what happened?
To increase it, it was more than 95% of the time in the turbulent region.
So it's a small region
Yes,
you have
very small.
dynamical regimes can be observed.
Yes, the transition is abrupt.
I have one. So, in this paper, you mentioned that you used for doing your simulations in the first part. I guess, this idea of getting these random variables from exponential distributions, it comes from them, I think, or not? I mean, in the sense that have you considered using random variables from different distributions to model these xi and yi?
I don't understand the question. You ask if it is a random process or?
So these x and y in the first part is where is when you put to your laminar and your turbulent regimes, you give them if you were above or below this threshold, but then you randomize. These are random variables that you get from this exponential distribution.
Yes.
And then with
in the
that,
model.
yeah.
Mm-hmm.
But you are using exponential distribution.
Yes.
What would happen if you use something else, for example?
The author told me that they tried with another distribution, but I don't know which one, and they found the same kind of behavior.
If no, I have one question. Okay, so if you increase your pump power at some point, is there any regime where you cross some critical value of the pump power, and then your distribution of this turbo of this linear time motion for the linear time is not power law anymore?
Just above the. It's possible, but it's hard to find the exact pump power value.
Yeah, more or less a pump power value. My point is that is there a regime exist above which, okay, in which this distribution of the time for the laminar motion will not be power law anymore? Then you can say that there is a crossover or a dynamical phase transition is going on.
Why do you say that?
I'm asking that if there exists.
We didn't observe it. We to answer, I should do perhaps another experiment with a lower pump power, but it's a delicate experiment because I change a little bit the pump power, so it's all quiet, or it's yes.
Is there any way to control your L2 value for the second part what you are talking?
Any way to control?
So you have in your simulation you have chosen different values of L2, right? So in experimentally, is there any way to control this value of L2?
These are the tests we have made to get these points, these experimental points. We tried various values of L2, and we let it go to see if they are stable or not. These ones are stable, but all the others are not stable.
Yes. So, any other questions? So if not, then let us thank the speaker once more.